All right, today's warm-up, we're going to start with something that should be a review from Algebra 2/Pre-Calc. We're going to be talking about this a little bit more in depth today and how it relates to limits, but I want you to try to find the vertical asymptotes of this function. All right, the pre-calc or Algebra 2 method of finding vertical asymptote. We'll review this a little bit today, but basically what you want to do is find the zeros of the denominator that are not also zeros of the numerator. In other words, what makes this function undefined but doesn't necessarily get canceled out when you factor it? So to find the zeros of this denominator, I would need to factor this. It would factor into x plus 5 and x minus 3. I'm going to go ahead and factor the top as well. We have two terms there, which means we're going to factor using GCF. So we pull out an x, and we're left with x minus 3. And what you will see here, if you remember our last sections when we talked about discontinuities, we have what's called a removable discontinuity at x equals 3. You can see how that sort of gets removed, it gets crossed out. So that would be a removable discontinuity. And then we have a non-removable at x equals negative 5, because we set these equal to 0 and solve them. The x equals 3 sort of gets removed because it's also a 0 of the numerator. Zeros of the numerator would be 0 and 3. Since that 3 is a 0 of the numerator and denominator, it gets wiped out. But the x equals 5 is a 0 of the denominator, but not also a 0 of the numerator. So that it turns out that non-removable discontinuity is in fact also a vertical asymptote. Remember, non-removable means you can't necessarily just put a dot, fill it in, and make it continuous. It means that either there's an asymptote or something weird going on there other than a little bit of a hole. So we're going to be talking about finding those today. This would be the algebraic way of finding it. We're also going to talk about what that means in terms of limits. So we're getting close to wrapping up our limits here. And today, like I said, we're going to apply that to vertical and horizontal asymptotes. We're going to start with the vertical asymptotes, and I'm going to give you two definitions for this. The problems that we're going to do on Delta Math, we'll practice both of these definitions. For the AP test, you do need to know the limit definition as well. And we'll also be doing an assignment from AP, from College Board, that practices these limit definitions as well. So the limit definition of a vertical asymptote is a function has a vertical asymptote at the point x equals a if the limit as x goes to a from the left of the function is either plus or minus infinity, if the limit from the right is either plus or minus infinity, or just the overall limit in general as x approaches some a is plus or minus infinity. Now in all of these, you might make a note that a is a constant. It cannot be plus or minus infinity. So basically, the limit as we approach a constant from either direction or from both directions, if it equals plus or minus infinity, then we can say that there is a vertical asymptote at that point. Graphically, what we're looking at here is, let's say we have a function that goes like this. So as we approach some a value, we'll call this a. As we approach from the left side, right, the negative direction, this is going up to positive infinity. So we'd say there's a vertical asymptote at a. Same as if there was one that maybe that went down like this. So we approach from the positive direction, coming in this way, it goes down to negative infinity. That would indicate that there's a vertical asymptote at a. Or if they were both happen to be going in the same direction, so if they're both going to positive, both going negative, we could say that that was a vertical asymptote. So that's how we use limits to determine vertical asymptotes. The algebraic definition is what we just used in that warm-up question. And we can say that vertical asymptotes of a rational function, because that's generally where we see vertical asymptotes, occur at the non-removable discontinuities. In other words, zeros of the denominator that are not also zeros of the numerator. For horizontal asymptotes, we also have two definitions we're going to talk about. First of all, the limit definition, which you will need to know for the AP test. And that is a function has a horizontal asymptote at the value y equals a if either of these two are true. The limit as x goes to negative infinity equals some value which we'll call L, or if the limit as x goes to positive infinity of the function equals L. And like before, the L in this one is a constant. So the thing that's switched in these two is for vertical asymptotes, we're going the limit as we go to some constant equals plus or minus infinity. In the horizontal, it's the limit as we get to plus or minus infinity equals some constant. This is actually kind of synonymous with end behavior. If you remember learning about that last year, basically what we're doing is finding the end behavior. And if the end behavior happens to be a number instead of positive or negative infinity, we can say that there's a horizontal asymptote there. Graphically, what this would look like is maybe we have a function that looks like this, and it's approaching some value we'll call L. There would be a dotted line, so it gets infinitely close to that value, and maybe the opposite direction. So here, as we're going to positive infinity, it approaches some L value. Maybe in the negative direction, it's a different one. Looks like this, some L value. So as we go to negative infinity, it's approaching some numerical value. Now, if it would happen that this was instead going down to negative infinity and not some value, then that would not indicate a horizontal asymptote. The algebraic definition actually relies on some rules that we learned when we talked about limits at infinity. So these are some shortcuts that we're going to use. Again, we actually outlined these a couple of lectures ago. To find the horizontal asymptotes, we're going to use the limit at infinity shortcut rules, which were, if the top degree is less than the bottom degree, then we have a horizontal asymptote at y equals 0. So let's say we have 3x squared minus 4x over 5x cubed plus 10. So the top degree is less than the bottom degree, which means we have a horizontal asymptote at y equals 0 because the bottom grows faster, takes the overall equation to 0. If the top and the bottom degree are equal, say 4x squared minus 10 over 3x plus 8x squared. So they both have highest degree of 2. We would take the ratio of the leading coefficients. If you remember that one, this would be y equals 4 over 8 or 1/2. So the same rules that we use for infinite limits, because that's essentially what we're doing. We're finding the limit as x goes to infinity of this function for all of these. If the top degree is bigger, if you remember the limit at infinity rule was, if the top was bigger than the bottom, then it was either going to be negative or positive infinity, right? That was always the answer. You had to plug in and figure out what it is. Well, based on that definition we just had, if it's either positive or negative infinity, that means there's no horizontal asymptote. So in this case, if the top degree happens to be bigger, there is no horizontal asymptote. Instead, there's something called a slant or oblique asymptote. We're not going to worry about finding those at the moment. That requires some synthetic division, which we're not going to worry about at this point in time. Just note that there is no horizontal asymptote. So those are our 3 rules. It's beneficial to memorize those because we'll have tests over this pretty soon. These same rules pretty much apply for limits at infinity and also horizontal asymptotes because they're kind of one and the same. All right, we're going to go ahead and apply these on a Delta math assignment. First of all, we're going to start with finding vertical asymptotes algebraically. So to do this is where you want the zeros of the denominator that are not also zeros of the numerators. So we can start by just finding the zeros of the denominator. There's actually no factoring that needs to be done here. So really there's anything we need to do. We just actually need to set this equal to 0 and solve it. And we get x is negative 4. And then we need to just double check that that's not also a 0 of the numerator. So when we solve the numerator, 5x is negative 3. So clearly that is not the same value. So this one is good. Again, the top is just a check that makes sure they don't equal the same thing, which would then cancel it out. All right, so that's all we have to type in for this one. Start off with an easy one. There's one vertical asymptote at x equals negative 4. All right. Next one here. This one's going to require a little bit more work. I always like to start with the bottom first. Try to factor this because we can't solve this directly. But there is two terms, which tells you that GCF is going to be our mode of factoring here. Pull out an x, and we're left with 2x minus 3. Now, you have two options from this point. One would be to go ahead and factor the top. To do that, you might need to make your big X, or however you choose to do that. We do the a times the c, and then the negative 17 at the bottom. And then this would be negative, let's see. Both would have to be negative. So negative 14 and negative 3 would give you that one. And then this would factor into 2x squared minus 14x minus 3x plus 21. Divide it, 2x times x minus 7 minus 3 times x minus 7. So it would factor into 2x minus 3 times x minus 7. Now, chances are you're not probably quite that good at factoring. You might be really good at factoring, and that might be super easy for you. You do need to know how to do that, but that could take you a bit of time. You can see here that these cancel out, and then we would just want that other one. The other way of doing this would be, well, we know our two zeros of the bottom are x equals 0. 2x minus 3 equals 0, so we get x equals 3 halves. And then what you do is you take these two, and then you plug them in the top and see if you get 0. So I plug my first one in, 2 times 0 squared minus 17 times 0 plus 21. That is going to give me 21. So we know that is not going to give you 0, so that means this is good because it didn't give me 0. And then I plug in my other one, 2 times 3 halves squared minus 17 times 3 halves plus 21. See what this equals. You should be able to evaluate this without a calculator. You would get 9 fourths minus 51 halves plus 21. That gives you 18 fourths minus 51 halves plus 21. So that'd be 9 halves minus 51 halves plus 21. And that would give you actually negative 42 over 2 plus 21. So negative 21 plus 21, which does give you 0. So since that gave you 0, you would actually need to eliminate this one because it is 0 of both the top and the bottom. Or alternatively, again, you could factor it. See that these cancel, and then so that just leaves you with this one, and that one is the one that equals 0. Both of them are actually kind of time consuming on this one, so take your pick. It doesn't matter. Both might take you a bit of work. So this one, it is x equals 0. This is, again, like a algebra 2 concept or pre-calculus. You can just do one more here if you would like. You always do need to factor the bottom because you got to find those zeros. Now on this one, though, what I would do, you can see 3 is in all of these. So I would actually just pull a 3 out first. That should make your factoring a bit easier. Just leave that 3 out there. And then it's going to be x minus 6 and x plus 5. So then when we solve this, this is going to give you x equals 6 and x equals negative 5. You don't need to worry about that 3 out in front. And then your two options could be, well, you could just take those and plug them into the top and see if you would get 0, or you could factor the top. When you factor it, it's x times x minus 8. And you can see there's nothing that cancels, so we are going to want both of these. There's no cancellation. Again, if you plugged them in, you would get 6 squared minus 8 times 6. So it'd be 36, like negative 12. Same as if you plugged in the other one. 25 plus 40, so that give you like 65. So in either case, it doesn't give you 0, which means we want to keep both of them. So we're going to say 2 vertical asymptotes, x equals 6, and x equals -5. Let's go ahead and look at the next section. This is going to be horizontal asymptotes algebraically. So this is where we're going to use those rules that I outlined, the same rules that we use for limits at infinity. We just need to compare the powers of the largest powers of the degrees of the numerators and the denominators. Big on bottom is y equals 0, same ratio of leading coefficients, and big on top means none. So really 3 easy rules. After you do some problems, you do get the hang of it. This one, biggest powers are the same. So we just do ratio of leading coefficients, which is 3. So we got 1 horizontal at y equals 3. Next one, then make it just a little bit more challenging for you here because it's actually factored out. You might be able to look ahead and see what the biggest power is going to be. If you are able to do that, you can see you're going to end up with a squared on the top and a squared on the bottom, which means we do need to know the numbers in front of those. When we FOIL this first one out, we're going to get x squared plus 7x minus 7x minus 49, and distribute the bottom 2x squared plus 14x. Now we do need to distribute this 3 in at least to the first term, because that's going to give us 3x squared. It doesn't matter what happens after that because we only care about the biggest power. And then the biggest power on the bottom is 2x squared. So ratio of leading coefficients there would be 3/2. Y equals 3/2. All right, another similar one. A little different one here. Well, all right, here we go. Okay, this one, if we look at the powers, top power is only a 1, bottom power, the biggest, is a 2. Bigger on bottom implies y equals 0 always. Always y equals 0. Because we know as we're going to infinity, this thing is approaching 0, which means there's a horizontal asymptote at 0. So that's really all there is to it. This next one, if you were to go ahead and do this one, when you multiply this out, you know that the biggest power is going to be an x squared because you're going to FOIL it. The bottom, the biggest powers are going to be a first power. So you don't even need to finish it. You just know that bigger power on top means no horizontal asymptotes. So there's an example of each. Let's go ahead and look at the last section, which will probably be the most challenging one. This one, you're probably going to need to refer to these limit definitions a couple times until you get the hang of it. The vertical ones, just note that x is approaching a constant, it equals infinity. The horizontal ones, x is approaching an infinity value, and it equals a constant. So they're two opposites there. All right, what we are asked to do is to identify all vertical and all horizontal asymptotes of this function. I like to start with the vertical ones because they're generally easier to spot. You can see that there is a vertical asymptote right here, sort of a dividing line there in the function, and that's going to be at x equals 3. There also is a horizontal asymptote. The most you could ever have is 2 horizontal asymptotes. Generally, there's only 1, but there could be 2. How we're going to figure those out is look at the end behavior. So look at this and look at this. This is going up to positive infinity, right? This one, however, is actually approaching a line right here. It's actually approaching that line, which is at -2. So there is a horizontal and a vertical asymptote on this. When we type this in, we have to give a lot of details here. We are going to state that there's 2 asymptotes, right? Let's talk about the vertical one first. The vertical one's going to be at x equals 3. And now we also have to give a reason why using limits. So our options here, it's the limit as x goes to 3 is negative infinity, x goes to 3 is positive infinity, or the limit as x goes to negative infinity is 3, positive infinity is 3. So those are our 4 options. So think back to what's happening here. As we're approaching 3 from the left, this is going down to negative infinity. And as we're approaching 3 from the right, it's also going down to negative infinity. So this is going to be the limit as x goes to 3 equals negative infinity is our justification. That one. This is a little bit challenging to just get the 2 straight here, but it really does help ingrain the limit definitions of these in your mind. Again, feel free to flip back and forth between those definitions. Vertical should always be limits approaching a constant equals an infinite value. Horizontal is limits approaching an infinite value equals a constant. So for the horizontal, these are a little bit harder to tell, but this is approaching negative 2 is our y value. And we're going to say it's the limit as x goes to infinity, positive infinity, because this is our positive infinity direction, right? We're approaching the y value of negative 2. So an infinite limit is actually synonymous with a horizontal asymptote. We'll do a couple more of these. This one looks interesting here. All right. Again, I always like to just note it the vertical asymptotes first because they're generally a little easier to see here. So we got one there at 6, one there at negative 2. All right, turns out there's actually 2 horizontal ones here as well. If we look at the end behavior here, it's definitely not going to positive or negative infinity. It's actually approaching this y value there of negative 1. This one's doing the same. So it looks like it's approaching negative 3. So I've actually got 4 asymptotes on this. I think this is the most that you'll have. Yeah, because it doesn't give you any more options. So we've got 4. We've got 2 verticals. Let's get those first. First one was at negative 2. And the reason why is because as we approach negative 2, it goes down to negative infinity. The second one is also another vertical here. That's x equals positive 6. The same reason, as we approach 6 from either direction, it goes down to negative infinity. Switch it up on us there. The next 2 are horizontal. Again, think of them as our end behavior. So our first one was at negative 1. And that's because the positive one, right? Positive infinity, limit as we get a positive infinity is approaching negative 1. And then the other horizontal was negative 3. And that's because as we go to negative infinity, it's approaching negative 3. All right, we'll do one more of these. Let's start with our vertical asymptote right here at 5. Our horizontal, we're going to look at the 2 end behaviors. This one's going up to positive infinity, so that is not going to be horizontal. This one is approaching a value there of negative 5, it looks like. So that is going to be a horizontal. Looks like we got 1 vertical, 1 horizontal, so a total of 2. There is a vertical at x equals 5 because the limit as we approach 5 is negative infinity. And we've got a horizontal at y equals negative 5 because the limit as we get to positive infinity equals negative 5. All right, be sure to reach out to me if you're struggling with any of these or limits in general, and best of luck.